All right, hello everyone. This is our lecture on atomic mass number, and isotopes. So let's begin. Um, we start with some definitions, and the first will be the term atomic number. This refers to the number of protons that you find in an atom. And if you remember a conversation that we had the other day and what you've read in your book, the number of protons is what defines the element. So for example, if there's an atom that has 26 protons, what element does it have to be? If you have a periodic table with you, or you have your book nearby, grab that, open it up, look at the periodic table in the back, and you'll see if you find atomic number 26, that has to be iron. Iron has 26 protons. Any atom that has 26 protons has to be iron. If it doesn't have 26 protons, it can't be iron. And I think we talked about an example with carbon. Carbon has 6 protons. Anything that has 6 protons is called carbon. All right, so that's the atomic number. It tells you the number of protons that you find in the nucleus, and it defines what that element is. The mass number has to do with how much the atom weighs. So to find the mass number, it's the number of protons and neutrons added together. All right. So, and as we mentioned before, an atom can have varying numbers of neutrons. Let's take an example here. If we have a mass number, of copper being 65. How many protons and neutrons does it have? Well, the way you solve that problem is that you have to know how many protons copper has. Remember, there's always one exactly right answer for the number of protons. For copper, what is it? Well, grab your periodic table again, find Cu, which is the abbreviation for copper, and look at the atomic number. That will give you the number of protons. And then you can subtract from 65 to get the number of neutrons. So copper always has 29 protons, and if the total mass number is 65, 65 minus 29 gives you 36. So there are 29 protons and 36 neutrons in this particular atom of copper. The mass number can vary from one atom to another because of the numbers of neutrons. This particular example that I gave right here had 36 neutrons. It's possible for an atom of copper to have 37 neutrons or 38 neutrons. There are different versions, different flavors. They're all copper. Remember, we talked about this the other day. They're different versions of the same element. So those are called isotopes. Variations in neutrons. This is kind of the definition. Variation in the number of neutrons is called isotopes. And actually, I gave some examples with carbon in the classroom the other day. Remember, carbon has an atomic number of 6, which means it has 6 protons. And then there's one version of carbon called carbon-12, which has 6 neutrons. There's another version of carbon called carbon-13 that has 7 neutrons. And there's a third version of carbon called carbon-14 that has 8 neutrons. All right, you see how that works? So there's different ways that we can describe or write notation to show atomic number and mass number. And this is probably the most common one, where we have this symbol here. And let's walk through what the different parts mean. The N right here refers to the mass number. Okay, that's that number we just figured out, the number of protons plus neutrons. The A refers, where's my cursor? There we go. The A refers to the atomic number, so that's the number of protons in the atom, in the nucleus of the atom. And then the X is the symbol for that element. All right, so here's an example. This is how we would represent carbon-13, and the way you say it is carbon-13. The way you write it is the big capital C for the symbol for the element. The number 13 refers to the mass number, and the number 6 refers to the number of protons. This is called nuclide notation. Nuclide notation. That refers to this way of writing something. So if you were asked to write a given element or a given atom in nuclide notation, you'd be writing something that looked like this. All right. So back to this idea of mass. If there are whole numbers of protons and neutrons in an atom, right? You can't have part of a neutron. You can't have part of a proton. So it is a little bit confusing as to why the mass numbers that appear on the periodic table are not in whole numbers. And as I mentioned before, and as you've read about in your book, this is due to isotopes and the fact that there are different flavors of a given or different versions of a given element. And each isotope of an element will have a different abundance. For example, most of the carbon that you find in the natural world is carbon-12. So it's very abundant. It has a high relative abundance, carbon-12. And carbon-13 is less abundant, and carbon-14 is even less abundant than that. So there are different levels or abundances of a given isotope. And so if you calculate, there's a way to calculate based on the number of isotopes and their relative abundance to find out what that atomic mass should be. Here is an example. So if you look at the periodic table, it gives you an atomic mass of chlorine at 35.453. Definitely not a whole number, so obviously there are some isotopes involved here. Let's see how you work that out. First, let's define this term AMU in case you haven't run across it in your reading. AMU is defined as an atomic mass unit, and that happens to be exactly equal to the weight of one proton. Okay, there are two isotopes of chlorine. One of them is called chlorine-35, and one of them is called chlorine-37. Chlorine-35 has an atomic mass of 34.969 AMU. And chlorine-37 has a mass of 36.966 AMU. And the relative abundances, you have to be given this kind of information in a question. The relative abundance of these two isotopes is 75.77%, so an abundance should be a percentage. 75.77% for chlorine-35 and 24.23% for chlorine-37. Now you notice the abundances have to add up to 100, otherwise chaos and madness ensues. So make sure if you're given these numbers, they should add up to 100. This is how you actually do the math. This is actually do this kind of problem. We take the first one, chlorine-35. Here is its atomic mass, 34.969, and we multiply that by its relative abundance. Now notice I turned the relative abundance from a percentage into a decimal. So relative abundance times AMUs will give you 26.496 AMU that comes from chlorine-35. And then for chlorine-37, here is its atomic mass, 36.966 AMU, times its relative abundance, 24.23%, right, expressed as a decimal. And you multiply those together and you get 8.957 AMU. You add these two numbers together, 26.496 plus 8.957, you get 35.453. And this is the number that you see on the periodic table. Now we're going to be doing some examples of this in an activity in a day or two, depending on when you watch this, and where you calculate these kinds of things yourself. So I want to show you this example here, and before we get to that spot. All right, that's it for this lecture. Thank you for paying attention.